we're going to be sharing the session, and we're going to start right away. The first paper is entitled Power Routing by Impedance Modulation. The presentation is going to be made by Sandeep Roy, who is with the Washington State University. Sandeep, the floor is yours. Go ahead.
Thank you, Sakis, for the introduction. Thank you to all the organizers for their flexibility. I'm so sorry I can't be there in person due to a number of factors. I'm very happy to present this work that is joint with Ali Merizisani, and we started this work back when he was at WSU along with one of my students, and also Sarah Rausch, who isn't an author but has been a contributor. And this is some work on taking advantage of power electronics to route power to proactively address weather events. And so, as all of you are very familiar with, the severe weather of various sorts, whether it's convective weather or winter weather, can have a substantial impact on the power grid, and the impact ends up creating significant costs both in the short term due to the outages and in the long term due to equipment related issues. So dealing with contingencies of this sort, whether weather related or other, requires thinking about and operating the power system in an emergency mode. And there's been a lot of work on how do you make the system more resilient. That's of two sorts. There's obviously efforts to physically harden the grid, but this sort of hardening becomes quite expensive and often is not easily feasible. North Carolina at some point did a study on taking everything underground, and the costs are not realistic. The other aspect is for whenever weather is projected to happen or happens, to manage the weather. And most of that is still done in a manual fashion and in an ad hoc and somewhat reactive fashion. And so the overall idea of some of the work that we're doing is, can you work from there and instead develop some systematic approaches to routing power and managing power proactively to mitigate some of the potential impacts of weather. As I mentioned, the overall idea of what we're trying to do is hopefully being able to reduce the impact of some large-scale events, weather events, by thinking about reducing power flows on lines that might be vulnerable to weather. And so winter weather in particular creates substantial numbers of outages, so do convective weather systems. And so it may make sense ahead of time to manage some of the power flows on those lines so that if there is a failure, the impact is more limited. So what does this mean? First of all, getting an idea of which lines are vulnerable or susceptible. And then secondly, if so, are there good ways to shift power away from lines that are congested or otherwise vulnerable and congested to ones that are less vulnerable? And this paper is really just a set of initial ideas on that last question. Power electronics, fax devices like SSSCs are making this feasible and cost effective. So modifying patterns of power traditionally has been done on the generation side, but that's both expensive and possibly slow. And so the thought process here is, can we instead work on use the fax devices? But to do that, we need to know how power flows would change when you use these devices or modulate them, and that's what this paper is really about. I'm motivating the work from the perspective of severe weather, but modifying congestion patterns is something that's important also during regular operations. This is coming from New York ISO, and a recognition that a lot of the lines in the central east part are often highly congested, and that incur some costs. And so the idea of using fax devices to move flow away from those lines is something interesting. Okay, so let me step away from the broad formulation and sort of get into the specifics here. we're imagining trying to do a design over some look ahead or horizon and our interval, and in general we assume that there might be some different possible futures of generation and load which are probabilistically defined, so in each future the generation and load levels are specified. What's important to our work is we're going to consider are a number of lines with series fax devices, and we're going to model those fax devices as allowing a change in the local susceptance of the line within limits. So mathematically, the idea that a local susceptance can be changed it can be captured in using as a modification of the susceptance matrix, and working through that, one sees that that's naturally written as a rank 1 type of perturbation to the matrix. And in this case, the idea is that for those tunable lines, we can change the susceptances within a range, and this parameter alpha is specifying that range. So we're interested in how these changes in line susceptances change the power profile or the power flows. We can figure that out by computing bus angles. For this work, we're using a DC power flow model, although at least some of the results would carry through to the AC case. From the angle differences, for this work, we consider a notion of congestion in the lines, and the congestions are the flow on the line relative to a rating, and that can be phrased in terms of the angles quite naturally. Our goal here is to try to use the fax devices to reduce flow or reduce congestion on a set of lines that are susceptible, and we consider that based on a metric V, which is adding over all of the target lines over the lines for which there's a vulnerability, the congestion or the square of the congestion metric. And so our goal is to try to minimize this. The ZQR is a probability of failure for a line, and the idea is that this would come out of weather forecasts and other things. It may be a low probability, but it's an indication that that line is vulnerable. When there's uncertainty in the flows or in the power profiles or the loads, we might average this metric over all of those profiles. So our goal here is to minimize the congestion metric with respect to the which are the susceptances of the lines that can be modified with the fax devices, and so one can directly, by substituting in the power flow or solution, in this case we're using the DC power flow solution, write an expression for that minimization, and there are constraints with regard to how much these susceptances can be changed. The form of the equation ends up relating to some graph structural notions related to the network, and so the slide gives the details, as does the paper. For a number of reasons, developing a numerical solution for this problem may not be the best way to work at this. A couple of the key reasons is that there's a whole lot of uncertainty in the formulation, and so it makes sense rather to try to get some simple insights into what the fax devices can do. There are also system scale problems and other things for any realistic size problems. Given all of that, in this initial work, what we tried to do was get some insight into what that optimum might be, and to do that, we work by analyzing the impact of a single susceptance, a single tunable parameter. So this is a sensitivity analysis of sorts, with the distinction that instead of looking at sensitivity to load or generation, we're looking at sensitivity to lines and line susceptances. In the solution to the power flow equations or the DC power flow equations, we noting that the line susceptance change is a rank 1 perturbation, we can write down an expression for the inverse of the susceptance matrix when there's a change in a single tunable parameter. When that happens, based on that, we can naturally figure out how the congestion is updated, and so the expression at the bottom of the page here gives an indication of that changed congestion. And so it looks like the nominal congestion with a term that depends on nominal parameters as well as the V's and U's, or just the locations of the lines that are relevant, and the nominal power profile, as well as how much we're changing. And so this is you could see this as a point-by-point sensitivity or a notion of change as the parameter is changed. One of the nice things about the way the congestion in any given line changes due to the susceptance change is that it's actually monotonic. One can argue that the sign of the derivative here is in only one direction, and from the monotonicity, if we're interested only in managing the flow on one target line, then we can do so very, very simply. Depending on which direction the sign goes, we either reduce the susceptance as much as possible or increase it as much as possible. And so the optimal is at the extreme. When you have more than one, so working from there, it's easy to put together a specific algorithm for finding the optimal for a given target line, and a given susceptance that can be changed using the fax device. This works through exactly that algorithm, which is it's a very simple numerically. Maybe more importantly than that, the paper gives details on this. This technique for optimization can also be naturally generalized to the case where there are multiple lines to where the flows matter, and the case where there are different probabilities or weights for those different lines. And so some more details of that are given in the paper. I won't give the details here, but I do know that using the monotonicity, we're able to get to an answer in that case. When there are multiple SSSC devices that can be changed, that gets even a little bit more complicated, and so there's a degree of search, but again, the monotonicity can help. The one other thing, which was a little bit beyond the scope of this paper that we did, was look at some graph insights into which directions the changes would be in, and so there are some ways to come up with directional and magnitude issues. I think I may be running late on time, and so I'll be brief. We worked through two examples, one in the 14-bus system case, and in this case we're looking at a target line and one line that has a device, and they're remote, so it's not immediately obvious which direction to change things to change the flow. Through the analysis that we used, we're able to do that, and one finds that increasing the susceptance here it allows an optimization of the power flow, and in fact there may be a change in the power flow direction for some of these cases. In the multi-flow case, we've also worked this through in a multi-flow case with two lines and gotten some answers there. We have also done a similar analysis.
Sandeep, 2-minute warning.
Okay, it sounds great. This is my last slide, so I think I can finish up. The plot on the left side, again, we're looking at a single flow optimization, and on the right side, a pair of flows, and we're able to go through and optimize the target line flow using the sensitivity or the rank 1 perturbation argument that we developed. And I'll caution that these work are very initial. We're working with a number of further simulations and hoping to get to further results, but we believe that this approach shows some promise in understanding modification of power flows using fax devices for severe weather or other purposes, and with optimization goals in mind. So I will stop there, and at the end of the session, I'd be happy to take questions.
Very good. Thank you, Sandeep.
Thank you.
We have time for one question. Go ahead, Patrick. Identify yourself because we do not know you.
Yes. Hi, Sandeep. Patrick Manciatici from RTE France. So thank you, Sandeep, for the very interesting presentation. Just perhaps...
Can you hear something?
I barely. I can hear a little bit, but not well.
Yes, okay. I can speak. Yeah?
Closer to the microphone. Okay. This one? Yep. Here, but you need this.
Talk very close to
Yes, Sandeep. Yes. So my question is it possible to add some uncertainty in load and generation in your approach or not?
Patrick, first of all, great to talk to you. Yes, in fact, in our formulation, the load and generation uncertainty is in there. We assumed a number of futures for load and generation, and so we're averaging that metric over all of those. Now, to be fair, in the simulations that we did, we never worked through that. Like we haven't done that case. At least when it's a single SSSC device, the optimization kind of solves in the same way. In the multi-device case, it gets a little bit more complicated. But yes, we're able to handle that, and we think it's important to be able to do that.
To be more specific, I have some doubt about the monotonicity, but...
Yeah, yes. So what you're getting at is the key issue, right? For when it's one line, I'm convinced that is possible. There may be some tricks, and you may have to look at multiple points, Patrick. But yeah, good, very good point with that.
Very good. Thank you very much.
Thank you.
Sandeep, stay tuned there.
Second last one. This one, Robert. No, Robert. So it's not working?
No.
You can use it as a pointer. Yeah. Yeah, so it's very nice to be here in Banff, very nice location. So my name is Robert Erickson. I come from the Swedish National Grid. And I'm presenting the work of Danilo Brown. He's my student, so he has done this work. And the work is about distributed HVDC emergency power control, and we're looking at the Nordic power system. So you're probably very familiar with the frequency response. So if you have a very large disturbance, you have a frequency dip. And in the Nordics, we are worried about the frequency minimum, frequency nadir, instantaneous frequency deviation, whatever you would like to call it. Another issue is also to have sufficient damping of this common mode after the disturbance. That is also important. What we have done once we get less inertia in the system with the remaining large disturbance is that we have implemented a fast frequency reserve. But we also have the opportunities of using the HVDC links that we have interconnected to our synchronous area. So up here we have the Nordic power system, and we are interconnected with UK by HVDC, so that's another synchronous area, and also the continental Europe, another synchronous area, and also the Baltic countries, which are also connected to Russia with HVDC links. So we have around 18 HVDC links that are interconnecting the Nordic power system. So what we have studied is to utilize the HVDC links to improve the frequency response, especially if we have, let's say, n-2 disturbance. And in previous work, we came up with a framework and agreed within Europe how to exchange this service. So how much power can we support and receive from the different synchronous areas? So in the Nordics, for over frequency, we can expect up to 1,600 megawatts. And so that's for under frequency, and 1,400 is for over frequency. So that could mean that, for example, if we have a large HVDC link on export, we could expect very high frequency. But the question is then, okay, how should we distribute these services amongst these all HVDC links? So we would like to receive as good response as possible in our system, but we would like to impact the other systems as little as possible. So then we started to look at the coupling between active power and reactive power. And there is a clear coupling when it comes to HVDC. So we have two different technologies. So we have the line commutated converter. So that's the old technology where you sort of have a natural coupling to the reactive power. When it comes to voltage source converters, you can independently control your reactive power, but usually you have the control in sort of voltage support mode, meaning that you have this coupling. Once you start to change the active power or you have changes in the voltage, you will also change the reactive power. So if you have a disturbance, you have this proportional support, so it's called emergency power EPC, so that was the droop frequency control. We have this coupling with EPCs to affecting the injected reactive power into the node where the HVDC is interconnected. It also means that the active power will change, but also the reactive, meaning that we will have a response from the load and losses in the system. So if we have voltage-dependent loads, we will have also that influencing the frequency response. So the starting point is then to look at a linearized model, just to see, okay, how are these correlated? What kind of pattern can we see? And then on top of that, we have the EPC, so this controlled HVDC. How will the linearized system look like? What additional terms will we get in these linearized equations? So then we looked at this coupling with reactive power. So we can derive these block diagrams for this, and then we can see that we have an additional term that is more or less change in reactive power over change in active power. So this term is then very important when it comes to the frequency response. This one in blue. Okay, but we are dealing with a large disturbance, so we cannot only look at the linearized model. We have to have nonlinear models to deal with. So in previous work, we have developed a future model of the Nordic power system, detailed model in Power Factory, where we have implemented this control together with other types of control with AVR, PSS, and so on, trying to represent the Nordic power system, and it's also published in a paper. So, as I said, when we have to deal with a nonlinear system, we cannot only look at the linearized equation. So what we see is that if you have the rate of change of frequency, so the integration of rate of change of frequency until the frequency minimum is then the frequency change. And very similar if you're looking at energy. So how is this EPC affecting the power of the loads and losses in the system? If you integrate that over time from the disturbance to the frequency minimum, you get a metrics of how your HVDC is influencing the frequency minimum. So it's shown in these two equations. And similar to the metrics would be then to look at the change in reactive power over active power and integrate that. And that can then be said to be a K factor that we are integrating until the frequency minimum. So if you look at this in a graph, you are comparing the case with and without this frequency support. So the difference between the reactive power support is then this red area. So that red area is then impacting the frequency response. So here are just two examples of the different technologies. The top one is the LCC. So this first graph is basically just the frequency response, and then here is the active power response. So those are very similar between the VSC and LCC, but when it comes to reactive power, they differ. So in the first case, when there is no EPC installed, the reactive power is as constant in the HVDC. Meanwhile, in the VSC, we still have this voltage support, so there is support or the change in reactive power to support the voltage, both when there is no EPC and when there is EPC. So we were then testing all these different HVDC links to see, okay, what will be the difference depending on the location and so on. And what we could see is that the LCC, if you're having that on import, you're also increasing your reactive power, meaning that your voltage will probably drop, meaning that you have help from reducing the loads, meaning that you get a better frequency response in the system. Meanwhile, the VSC is sort of supporting the voltage, so you don't get this additional support from reducing the voltage and that you reduce the loads due to that. So here we have a list of all these different HVDC links that are interconnected in the Nordic power system. So we're testing with the same droop, so megawatt per hertz, to compare the effectiveness of these different HVDC links. And the graphs here are then showing a bit about the response. So this one is showing the different HVDC links again, and how the loads and losses are changed due to this EPC. So each and every HVDC link is then assessed that, okay, in this case, the first one, then the loads are changed by 100 megawatts, for instance. So it's a reduction of 100. So what we could see is that in the upper graph here is that if you have less voltage support, you actually get a better improvement of the frequency minimum. So it's better to not have voltage support when it comes to EPC in that sense. So we were then looking at, okay, what are the different options that we could select? So the first one, we saw that, okay, if we were to select these 4 HVDC links, we don't get that good response. Meanwhile, having this second option, we get a much better frequency response. And the difference is actually around 25%. So meaning that if you go for the better option, you actually use around 25% less power on these HVDC links, meaning that you affect the other systems a bit less. So to conclude is that, I mean, to be able to perform this type of study, not only a detailed model is needed, you also need to look at the different areas where you have disturbances, but also look at what type of load models do you use to have an accurate representation of the load models. And in general, it's better to use LCC HVDCs that are on import to improve the frequency minimum, and that VSCs HVDC links are improving the voltage, meaning that they are not so much improving the frequency response. Of course, you have the active power, and the active power is, of course, improving. So that doesn't really depend if you have active power from VSC or LCC. So thank you very much for your attention.
Thank you, Robert. We have a question for time for one question. Go ahead, Kostas. Introduce yourself.
Kostas Vournas, National Technical University of Athens in Greece. Just a quick clarification. What was in your simulation, what was the effect on the neighboring systems in terms of megawatts at the maximum? I saw you had several lines going up 150 to 200 megawatts, but if they were in the same system, how much of the support came from Europe, how much from the other systems?
In this case, I think it was around 1/3 coming from UK and 2/3 coming from continental Europe. And since this disturbance was around 1,400 megawatts, and we had the frequency reserves and primary frequency reserves in the Nordics, I think we were using up to 300-400 from the continental European system, and then 200 for UK system.
That's a big disturbance also for you.
Well, I mean, a bit, but it shouldn't happen too frequently. So hopefully.
Thank you very much, both. Okay, we move to the third paper entitled Enabling Undergrounding of Long-Distance Transmission Lines with Low-Frequency AC Technology. Will be presented by David Seloff, who is with the University of Wisconsin in Madison.
Good morning, I'm David Seloff. I'll be presenting this work that I did during my PhD with Lena Rold at the University of Wisconsin-Madison. I'm currently at Argonne National Lab, and I'd like to thank them for the support to be here. So I'll be talking about undergrounding and analysis for undergrounding with long-distance transmission lines with low-frequency AC technology. This is motivated by an increasing share of underground lines that we are seeing in current years and expect to see in the future. This is largely driven by an increase in very costly natural disasters. This plot shows the frequency of a number of natural disaster events that have exceeded $1 billion inflation adjusted in US dollars in the last 40 years, and there's a marked increase. And the cost of these events has also increased. This has been attributed to several factors, including an increased frequency of these events due to climate change. There's also increased exposure of assets. We can think of that as value that's at risk to these events, along with vulnerability of these assets, fragility of the assets and the systems as well. And so these immense costs have led to an increased consideration of costly undergrounding projects. So for example, in Florida, where there are a lot of tropical storms, there's been a significant increase just in the last 2 years of a number of undergrounding projects and the investment put into undergrounding. And on the other side of things in California, where there's a lot of wildfire risk, both for ignition due to power lines and vulnerability of power lines, the utility has committed to a very aggressive plan of undergrounding 10,000 circuit miles in the coming years. So these are excellent mitigation strategies, but they come with operational challenges. So we know that compared to overhead transmission lines, there's much larger capacitance in these underground cables. And this limits power flow and causes voltage issues. There are also second-order effects, like skin effect and proximity effect. There are also losses in the metallic sheaths due to induced currents. And then there are also stricter thermal limits in underground cables. That's due to the absence of convective cooling, the runaway thermal effects, and also constraints on thermal expansion in the cable ducts. So this leads to some constraints related to the length, the capacity, and voltage considerations in undergrounding of transmission infrastructure. These properties certainly depend on the dimensions of the cables and the material properties, but they also have a strong dependence on the frequency. So what we're going to focus on in this presentation is that there's a potential to mitigate many of these effects by choosing a frequency to operate these cables lower than 50 or 60 hertz. And this falls under the area of research known as low-frequency AC transmission. This is a concept that has been discussed for many years. You can see just some examples of papers going back to 1899, in fact, discussing this concept. Some of the advantages in the context of underground cables are a reduction in the charging current due to the mitigation of the capacitive effects. This also leads to an increase in available active power flow on these cables under the same thermal limits. This also contributes to a reduction of losses, along with the reduction of the losses due to induced currents in the metallic sheaths. That's another factor reducing losses. Another aspect that's talked about most significantly is mitigation of angle limits, which we won't discuss at length here. Another benefit that we get is increased power flow control in the system, not only on the cable that is selected or set of cables selected for low frequency, but also at the terminals of the converters that we use to convert the frequency. We can control active and reactive power at those converter terminals. Another distinct advantage is that this lends itself naturally to multi-terminal systems. And that is largely due to the availability of protection equipment that, for example, at 16.7 hertz, there is some switch gear available for certain applications. So this could be brought in the near future into low-frequency AC systems. So our goal is to quantify the performance of these systems with low-frequency AC cables using an optimal power flow framework. And to do that, I'll first go over the existing model that's typically used for low-frequency lines, and this is used for overhead lines. So it is to take the distributed parameter model, consider the susceptance and reactance as linear functions of frequency, and then assume that the resistance and conductance are constant values throughout all frequencies. We lump these into a lumped parameter pi equivalent circuit, and it looks like this model here. And this has been shown to perform well and be accurate for low-frequency overhead transmission lines by several papers. But it doesn't perform so well. These assumptions don't hold for underground cables due to the second-order effects that I've mentioned. So we need to take this model and modify it for cables. So we take the lump parameter pi model, and we look at each of these 4 impedance parameters individually. We look at a detailed classical model that takes into account the differential equations for interactions between the central conductors, the outer sheaths, and between phases. We solve this detailed model, which is intractable for an AC optimal power flow. We reduce it to a single-phase equivalent model, and we plot the results in orange here for this detailed differential equation-based model for each of the 4 parameters. And then we take that and we fit an approximate model based on polynomial functions of frequency for each of these parameters. And the first thing that you might notice is that for the first and the third plot, the resistance and the shunt conductance, assuming a constant value of these parameters across all frequencies is not a good assumption, and that's why we need to do this extra model fitting step. And we're able to fit these parameters with fairly good accuracy. With these polynomial models. Here's just an example. The plot that you saw was a 135 kilometer cable. It tends to underestimate slightly at the higher frequencies. You can see that there's a relative error of up to about 7% with the shunt conductance, which is the most nonlinear looking one in the third plot. But as we go to shorter cables, the model becomes much more accurate. We see much lower errors for a 22 kilometer cable, for example. So we can always break these lines into smaller segments if necessary. So with that model, we're able to represent the AC power flow equations as functions of frequency for each of these 4 parameters. So these represent the AC power flow equations. The full details are in the paper, of course. We can do this for underground lines, underground cables, and for overhead lines. Then we fit this into our AC optimal power flow model. So we start with the standard ACOPF, minimizing generation cost. When we incorporate these equations into the power flow equations, we have frequency as a decision variable in this model. And then the power flow equations have these frequency dependencies. The additional difference that we add into this model is, as I mentioned, the capability of the frequency converters to inject active and reactive power at their terminals. So this shows up as this PI term in the power balance equations. So with this, we're able to capture the behavior as a function of frequency and analyze what system performance would look like with LFAC cables. So we analyze this in a very simple stylized test system using the RTS GMLC system. This represents a case where at a very simple level we might have a utility undergrounding a large portion of an interregional transmission corridor along with some intra-regional transmission as well. So we choose this 230 kV line subnetwork. We isolate this with converters for the LFAC case, and we consider that all of these lines shown in green are underground cables. We also isolate this from any generation and loads, which is an important point that we would not have generators or loads operating at this lower frequency. And we take the parameters for these cables for these standard 230 kV cables from a manufacturer data sheet and apply the cable parameters to our model and calculate the frequency dependent model. So then we were able to solve the optimal power flow problem. First, we consider the case where we don't have any low-frequency AC. We're just undergrounding these cables and not doing any conversion of frequency. This is at 60 hertz. And we don't find a feasible solution in that case without any of the compensation or frequency conversion. But then we consider several scenarios where we add these converters to change the frequency. First, we allow the frequency to vary between 0.1 and 60 hertz. And we find an optimal solution at a low frequency of 6.8 hertz. Next, we fix the frequency at 16.7 hertz, which is a standard frequency for this type of low-frequency network. And we find a solution that has a very, very similar cost. So we could consider operating the system at this frequency. And finally, we fix the frequency at 60 hertz, and we do find a feasible solution that's slightly higher cost. This shows us that the power flow control, the active and reactive power injection from the converters, allows us to find a feasible solution where we couldn't at 60 hertz without the presence of these converters. And finally, we use the same model to analyze the HVDC case. And there are more details in the paper about how the model extends to HVDC, but we get a very similar result for DC. So this is one result showing us that low-frequency AC can be very comparable to HVDC. And finally, I'll show a sweep across frequencies. So we fix the frequency at distinct points and show how the generation cost changes for these different fixed frequency values. And this just shows a few different cable models, a copper conductor and aluminum conductor. The optimal frequency is shown at this 6 hertz. And we see a significant increase above about 40 hertz. And that, looking a little bit more closely, we see that there are larger losses, especially on these cables at that higher frequency range due to these second-order effects. And that also requires additional generation. And so looking at, there's an expensive natural gas generator that it operates at a constant load between 0 and 46.6 hertz. But then as we increase the frequency above 46.6 hertz, that generator is relied on more and more because of this additional need for generation. And I would also mention that generator is right at the downstream end of the cable network. So we can see here in this stylized, simple example, some of the cases where we might want to consider low-frequency AC and why we would consider lowering these frequencies to get these benefits. So to conclude, we've seen that it's important to parameterize our model as a function of frequency for both real and imaginary impedance parameters when we're studying power flow at non-standard frequencies. So we present a polynomial model for this. And there are some advantages that we capture in our AC optimal power flow formulation. This includes reducing the losses, increasing capacity for active power flow, and gaining power flow control. And we show that there's performance very comparable to HVDC, where we may have some advantages of LFAC are in the areas of protection systems or utilizing existing infrastructure lines and cables. And so it's worth considering for its comparable performance. Future work includes combining this model with a more detailed economic analysis, making our analysis more detailed and robust, including optimizing the decisions of where we put these underground lines and the LFAC converters. And then there's a lot of room for application, such as offshore wind farm design, reliability, resilience assessment. So thank you very much for your attention.
We have time for one question. Let's say, Ilu.
really happy to be chosen. Thanks. I have a quick comment. There's a professor at Xi'an Jiaotong University in China. He spent half of his lifetime studying low-frequency transmission, not necessarily underground, and the choice of his frequency is 16-some hertz. I don't know if you know about that work. That seems complementary to your work and maybe quite, revealing. He did a tremendous study economically and as well as parameters and feasibilities. Yeah.
Okay, thanks for that comment. I'm aware of some work that goes back to the 90s about looking at long-distance transmission across China. I'd be happy to talk more and make sure we're thinking about the same things, but that's a great comment. Thank you.
David has been very good in keeping time, so we have time for another question. Spiros, introduce yourself.
Great, thanks. So Spiros, from DTU, thanks for this nice presentation. I have actually maybe two small questions. The one is, you found that it is infeasible without LFAC, so low frequency AC. And I was wondering, did you consider reactive compensation? That's the one question. The second is, you said that this can also be for offshore wind farms, and indeed, actually, Denmark is trying to build this artificial energy island. So we looked into this low frequency AC as a solution or alternative to HVDC connections. And we found that the cost of transformers is too high. I mean, it's a break even. At the end of the day, the cost of transformers is so high because the iron core is much larger, right? So we didn't find, I was wondering what you think about that.
Yeah, that's a great comment. So the first question about reactive compensation, that's a great point, and we've been considering that. We haven't looked at that in this case, but it makes a lot of sense, and I think it's a good topic for future work, doing a more detailed comparison. And then for offshore wind, that's also a great point. I know there have been some detailed techno-economic studies about offshore wind and the possibility of low-frequency AC, and maybe you've been involved in some of those. I think the system topology depends. That dictates a lot of these considerations. I know some of the work has considered different frequencies and how that would affect transformer sizes, or can we get around having low-frequency transformers because the size scales with as much as you're reducing frequency. So that can be a significant cost. But I would say compared to DC, there may be some simplicity here in some of these systems. I won't say that it's better than HVDC, but I think it's worth comparing in more detailed analysis.
Thank you very much, David. Okay, we move to the fourth paper of the session. It is entitled Exploring Reactive Power Limits on Wind Farm Collector Networks with Convex Inner Approximations, and will be presented by Maz Almasalki from the University of Vermont.
Thank you. Oops. Alrighty then. All right. Has anyone else seen the mouse that's crawling around under the tables?
It's a squirrel.
Squirrel. Has anyone seen it under these tables? No. Okay, good. Now you're awake. So I will be presenting a topic and a work that Nawaf has actually done. This was supposed to be my talk. The other two talks were because of absencees. So I will be presenting this talk. It is Nawaf's work. I'll let him and Ian answer all the hard questions. Ian is off on a gondola ride, so you should definitely give him good questions. The funny story with this paper is this was an idea that came from the last conference I went to before COVID in Nice, France in 2019. And so this finally now is out, and due to the hard work of Nawaf. One of the topics, one of the reasons for doing this, why are we looking at wind energy? And that's basically to mitigate climate change. We know we're going to need a lot of renewables to bring carbon emissions down. And that's going to require terawatt scale renewable integration. We know that's a power systems challenge. And to solve that challenge, we need to think about what the wind can do for us. And so luckily, based on the news I saw yesterday, it looks very likely that the US will double its wind capacity between today and 2030, which is really exciting. All right, so why do we care about more wind energy? Why is it interesting? It's because it brings reliability challenges. Specifically, we're interested in having these wind farms take a more active role in regulating voltages and support transmission system operations. And specifically, their capabilities of these wind turbines really revolves around reactive power support. And so the question we wanted to answer in this paper was, if you have a network of wind generating turbines, how much reactive capability, how much reactive power support can you get from this wind farm topology, or from this wind farm network? And the real question we want to answer is not the individual turbines, but what can the network as a whole produce given the constraints of the network itself? And so we know from lots of papers and lots of work what an individual wind turbine can do. It's called reactive power capability curves. They're limited by currents and voltages. And so we have this relationship between active power and reactive power. And what we want to try to think about is how do we create something similar but for the entire wind farm? And so, of course, you could just take a naive approach and just sum up the reactive power capabilities of individual turbines, but of course you're then neglecting the actual underlying networks and the physics. And you also have local control systems that will prevent those turbines from delivering the reactive power that they are rated at. And so what we're trying to do here is incorporate the AC physics of the underlying network to understand what the network can do as a whole. And so it's a difficult problem to solve. It's a non-convex program. And so what we're going to do is we're going to apply some of the tools that Nawaf developed during his PhD on convex inner approximations to basically understand what is the admissible set of reactive injections that these wind turbines can deliver without violating any network conditions. And so to talk about this, consider a simple 3-node system. We'll do the other network later. And so you can describe this very simple collector network through the disk flow equations. And as Nawaf mentioned yesterday, this is linear equations except for the relationship between currents and power line flows and voltages. And so you have this non-convexity. And if you wanted to plot, if you look at the space of injections and reactive power injections from one turbine and the other turbine, all the blue dots represent admissible injections that do not violate network conditions. And where it's white, it basically means you're going to violate network conditions. And these are voltages and currents, limits on voltages and currents. And so you could, for example, say, well, let's operate our networks. Let's find operating points along the green line. And in that case, we would always be admissible. If you operate along the blue line, the red line called B, if you operate around the red line, if you get to this point, you will become inadmissible unless both turbines basically avoid the hole. And so that requires coordination to avoid this hole in the middle. And so coordination between different turbines requires basically communication between them. And so what we're trying to do here is, can we essentially decouple the actions of the turbines and describe the reactive capabilities of each of these individual turbines. And that's going to be useful later for a disaggregation problem. So we're basically going to see what can the individual turbines do under the network assumptions. And so what we're really trying to do is trying to find these hypercubes inside of the admissible set for these wind turbine networks. And to find these hypercubes, a non-convex program, basically we have to replace this non-convexity. And as Nawaf showed yesterday, that can be done through convex envelopes. And so you can basically eliminate your non-convexity by creating lower and upper bounds. This convex envelope gives rise to these proxy variables that replace the actual physical active, reactive, and voltage variables with proxy variables that create upper bounds and lower bounds. These bounds, these envelopes, upper bound and lower bounds on the non-convexity can be defined explicitly through a second-order Taylor series approximation. Taylor series approximations, because we're using a second-order Taylor series approximation rather than a first-order, we get really good, very small, very low errors, which indicates that the bounds are actually quite useful. And so what you can do is you can then take away your physical parameter and replace it by what we show in some of the preliminary work. You have a lower bound that's affine, you have an upper bound that's convex, and so you can eliminate your non-convexity with these convex envelopes. And so you can redefine your dist flow equations for your network through an entirely convex formulation, and this is an inner approximation because you've essentially created these proxy variables which over and underestimate what the actual physical system is doing. And so as long as your over and underestimates are within their limits, you know the actual system is within their limits as well. All right, so then we go back to the physics. We have a convex inner approximation of the actual physics of this network, and now we can go ahead and we can maximize the reactive power capability of this network. And we know that whatever values we get here will ensure that the actual network conditions are satisfied. And so we can create essentially the maximum reactive power limit. We can find that. We can find the minimum reactive power limits at each wind turbine to give us the upper and lower bounds on the head node reactive power output. And that gives the network's reactive capability curve. And so you can take this network, so this was a network I think Ian gave us. I forget the exact origin of this network. And so you can look at, for different active or wind patterns, for different generation patterns, active power generation, you can see what the reactive capability of the wind farm topology is. And the losses up here are due to line losses. So the reason you can't deliver everything is due to line losses. And then later on, you get a reduction in your reactive capability due to voltage constraints in the network. All right, and so the question is, if you have, for a given active power profile from these wind turbines, how do you essentially disaggregate or allocate the reactive capability to the individual turbines? And so by solving this problem, we also get these reactive capability values or allocations for each of the turbines in the network. So this is the nodes in the network, and this is the reactive capability of each of the individual turbines, which sum up to the network's entire aggregate capability. And so we provide aggregation, but also disaggregation through this approach, which then means you have these Q plus values and Q minus values for every single turbine in your network. And so if you want to change the wind patterns, when you change the wind patterns, you get, of course, different capabilities. And so in this scenario, all the wind turbines are at rated active power. So you have less reactive capability available for you. And as you set some of the wind turbines to 0 for some reason, and other wind turbines at their rated power, you're able to generate more reactive power. And so so one obvious question, and something that I think Line asked as well yesterday, when you're dealing with convex restrictions or convex inner approximations, clearly we're cutting out parts of the actual feasible set. And so how conservative is this convex inner approximation? And so now after some really good, I think, fair comparisons with a purely NLP approach, a convex relaxation approach, and then some of Ian's former or early work on reactive capability. What did he do? He didn't do an optimization-based approach. He took a corrective control approach to explore the boundaries of these networks. And so what we see is that the convex inner approximation produces a range -10 to 7 for scenario 1 and -10 to 8 in scenario 2. So that's very similar to the nonlinear model. It's very similar to the convex relaxations, and it's not too similar from what Ian's past work showed as well. And so what we can claim is that these convex inner approximations, despite being a restriction on the feasible set, actually are not overly restrictive and quite practical. It also has other properties that when you work with convex inner approximations, anywhere inside of this green box, you guarantee that a network of conditions are satisfied, whereas a nonlinear approach or convex relaxation actually does not guarantee that, due to the presence of potential holes in your feasible set, or if you operate out here, which is outside of the feasible set. All right, so the Q, how much time do I have? 5 minutes? 5 minutes. Wow. Okay, good. So there's time for lots of questions to now on. So now that we have these Q pluses and Q minuses for each of the turbines, we can then use these Q pluses and Q minuses to solve the disaggregation problem, which would take potentially a voltage regulation problem where you have some kind of disturbance on the grid where the network needs to deliver some reactive power to essentially bring the voltage back to the set point. And so when you do this, you have a bunch of turbines you need to control, and you need to find the set points for these turbines to know how much of the total reactive power from the network do I need to disaggregate or allocate for each of the individual turbines. So this disaggregation problem we need to solve. And through this mechanism, because we know what each of the individual nodes can deliver within network-aware conditions, we can effectively disaggregate any QRef value. So whenever your QRef needs to be, we can disaggregate into the individual turbines through this very simple policy, which basically takes the total requirement divided by the total available injection or absorption, consumption of reactive power, which would be this term here or this term here. And the min terms in here deal with the fact that a turbine can't exceed its value, its individual value here, which is Q plus. And so if QRef is larger than the sum of the Q pluses, then you basically will saturate at Q plus. So what we're going to do now is we're going to apply this disaggregation policy here. We're going to subject a disturbance from the grid and see how the wind farm topology basically recovers the voltage. Boop. All right. So basically you have a step disturbance in your network, which is sustained for some period of time until the grid recovers. And so you have the step disturbance and a ramp recovery. And the voltage at the point of common coupling is the red line here. This red line is achieved by reactive power responses from the individual turbines. And you can see here that the blue line, the reference that's being commanded from this control loop is the blue. We're able to deliver exactly what is being asked because we know what we can deliver. Because of the network constraints, because of the individual turbines' reactive capabilities. And so we can show that when the disturbance happens, we can deliver reactive power. We can keep the voltage within the network. These are the individual node voltages within the wind farm network. We can show that these voltages are all within their limits for the duration of the event. When we have the ramp recovery, we're using a static model to deliver these reactive capability curves. And a static model cannot guarantee that during transients we don't violate conditions, future work. And so we get a slight overshoot due to unmodeled dynamics in the ramp recovery. But the key part here is all of the line voltages are within their limits. We're delivering reactive power to support the voltage here, and we're not violating the local wind farm topology network. The gap you see here is the gap from the convex inner approximation being conservative. But that gap is not very large. It can be improved, of course. Yep, thanks. And so another approach you could have taken is basically you basically just deliver the reactive power you need to drive the voltage all the way up. If you take this greedy approach where you satisfy your grid conditions and you drive the voltage up to its reference, you end up requiring more reactive power than you have and you have the reactive power, but you end up violating your wind farm network voltages. And so you're not taking into account the fact that your network topology has physical constraints as well. And so you can compare and see that if you have a greedy approach, you basically overload your network in certain areas, which would then kick in protection. And so this policy is not even implementable, whereas in this implementation, you can actually see you could implement it without violating a network condition, without driving protection. And so winding down, you can see that we have adapted convex inner approximations. We've adapted to three-phase balanced wind farm collector networks, which is where the disk flow model is viable. We can characterize this network's reactive capability, and we can use the reactive capabilities and the disaggregation policies to actually perform voltage regulation to support transmission grid operations. Next steps, of course, are plentiful because this is relatively nascent work. And so we could look at the role that topology plays in the reactive power capability. We could look at comparing the method to what's being used in industry today. We would love to get access to more realistic models. And then we're very interested in understanding the role the protection system plays and managing the dynamics as well. It's not really cool to see we'd love to find a way of basically shaping the reference signal so we don't actually violate during transients as well. So that's all I have.
Thank you very much, Matt. We have time for questions. Kostas, go ahead. Yeah. So we have 3 questions. So let's see if we can handle it.
National Technical University. Can I have one of your first slides where you show the two wind turbines connected to the same feeder? I think one reason why you have this problem that you showed with the hole inside the feasibility region is because you use the same Z to transmit twice as much power. They would never do it in a real farm. It would be, the first one would be Z by 2, and then this would completely go away. Okay. At least in the farm that I have made detailed analysis with 10 wind generators in 2 feeders, we never had any problem of line overload because these cables are always a bit overrated.
So the line overload or the voltage overload?
No, voltage overload is always at the end of the line, so there's no problem there. But I see that you have a problem with line overload in your 0-1 line because it's taking double the power with the same Z.
Okay. Yeah.
So probably I think it's a good work, but maybe
it's a toy example.
In practice, it will not be met.
Okay, that's good to know. Thanks.
Next one, Claudia.
Claudio Canizares, University of Waterloo. First, apologies for missing the session this morning, but I was right IEEE board meeting, so this morning it's from 7. So I'm a bit groggy. So let me ask you a question about the convex approximation. How do you guarantee that you capture the feasible area in general? Maybe on this problem, but in general. And how do you guarantee that it's actually not conservative, other than the test you run? Is there any more generic analysis? Thanks.
So I think the first question was, how do we guarantee it's an inner approximation? And that's because
It's feasible, yes.
So we guarantee it's feasible because our bounds on the envelope, the convex envelope on the non-convexity, the non-convex term, the convex envelope ensures that if your proxy variable for line flows, so if you can see it here, the proxy variable for voltages, if your upper bound on voltages is within the limits and your lower bound on voltages is within the lower limits, then you know that your physical voltage is between these two. So if your proxy variables, which are extremes, are within limits, then you know that your physical variable, which is between the extremes, is also within limits. So because of the envelope, you guarantee feasibility. On conservativeness, that's a very good question. So we do not have guarantees that it is non-conservative. So these results are illustrative, not guarantees. So as far as I know, there are no guarantees that convex restrictions or convex inner approximations are non-conservative. It depends on the curvature of your non-convexities and the network you have. So there's some nice work by Line, Dan, and Dongchang Li on transmission networks, looking at convex restrictions, that show similar practicality of these convex restrictions and inner approximations. And so there's no guarantee in general, but there are certain properties that we can take advantage of, and monotonicity is one of them, which we leverage in our detailed work. So the mathematical tools are in here, are in this paper. And so we enforce monotonicity conditions, and as long as those are valid in the region of interest, you will get a pretty good approximation. That's a good question.
Well, thank you. I know there are a couple more questions, but please hold your questions for the panel discussion. We're going to move to the next paper, the last one, which is a joint paper between Argonne National Lab and Georgia Tech, close to my home, and will be presented by Lisa Cody. The title of the paper is Optimizing Transmission Infrastructure Investments to Support Line De-energization for Mitigating Ignition Risk. Alisa?
Okay, hi, my name is Alyssa Cody. I'm a postdoc at Argonne National Lab. And this is a joint project with Ryan Paninsky and Daniel Molzen at Georgia Tech. So California electric infrastructure is responsible for less than 10% of wildfires, but these fires consist of roughly half of California's most destructive fires. And this may be due to the fact that conditions for large wildfires, like high winds, also seem to align with conditions for ignitions via electric infrastructure. And to reduce the risk of wildfire ignition, utilities proactively de-energize power lines during times of high wildfire threat, and these de-energizations are called public safety power shutoffs, or PSPS events. So utilities will identify some subset of lines that are deemed too risky to stay energized, but these de-energizations will often lead to an inability to serve all the load in the network. Therefore, we have this trade-off between reducing wildfire risk and serving load in the network. And as I'm sure you are all aware, and David mentioned as well, that future conditions are forecasted to be more conducive to wildfire ignition. Therefore, these de-energization events are likely to continue for a long time. And PG&E, in their 2020 wildfire mitigation plan, said that their goal is to make these PSPS events smaller in scope, shorter in duration, and smarter in performance. And one method to achieve their goal is through infrastructure investment. And David also mentioned this, but PG&E has plans to underground 10,000 miles of power lines. There's also investments from the state government of California, as well as the Infrastructure Investment and Jobs Act from the federal government. So this leads to the question, how should we invest in infrastructure to reduce wildfire ignition risk and load shedding? So the goal of this project is to optimally select site and size infrastructure investments to support system operations during PSPS events. And we're specifically looking at transmission systems in this project, and we consider 3 different types of investments. So the first are grid-scale batteries. We look at line hardening, undergrounding lines, installing covered conductors, and doing intensive vegetation management, and also installing solar PV. So ultimately, we want to know where to install batteries, solar PV, and hardened lines to optimally balance this trade-off between wildfire risk reduction and load shedding. And there are other works that look at infrastructure investment or operational changes to reduce wildfire risk, and our work builds on this paper from Noah Rhodes in 2020. So this is their paper here, and today utilities often de-energize lines using thresholding methods or using expert advice. And in this paper, they show that optimizing de-energizations outperforms thresholding heuristics in that you can achieve lower wildfire risk and lower load shedding. So this is an extreme simplification of the optimization problem that they're solving, but basically they're looking to minimize a weighted sum of load shedding and wildfire risk, where this alpha parameter is a trade-off term, and if alpha is equal to 0, this means you're only interested in wildfire risk reduction, and if alpha is equal to 1, you're only interested in load shedding reduction. So in our paper, we define wildfire risk as the sum over all lines of a risk parameter R defined per line, times the energization variable z, where z is equal to 1 if it's energized and 0 if it's de-energized. And we assume that the line poses no risk if the line is de-energized. And anecdotally, we found that solving these types of problems can be very computationally challenging. And it may be the case that these wildfire switching problems are more computationally challenging than traditional transmission switching problems. And I can give a quick explanation as to why that might be the case. So here's the wildfire switching problem that I just posed, and here's a traditional DC transmission switching problem where we're now minimizing over cost. So if we let F be the power flow on a line, it has to abide by these thermal limit constraints. And then, because this is a mixed integer linear program, we're going to use branch and bound to solve this problem. So binary variable z is going to be relaxed to a continuous variable. And then this fractional solution of the power flow over the power flow limit satisfies our thermal limit constraints. And our objective function inside the wildfire switching problem actually incentivizes the use of this fractional solution over the binary solution z equal to 1. So the branch and bound algorithm may encounter many of these fractional variables during solving. So in this project, we looked at optimizing investments simultaneously with these optimizing these line de-energizations. So this is all to say that we've created a very difficult problem for ourselves to solve, and I'll talk a little bit more in future work about how we could potentially make these types of problems more computationally tractable. So here's our problem formulation, where now we have included these constraints for infrastructure investments. And we place our investments via a worst case representative 24-hour period. And this is a multi-time period formulation, and these constraints allow it to remain a MELP. So our objective function still has a load shedding component, and this is a multi-time period load shedding component. And now in our wildfire risk term, we still have our energization, line energization variable, and now we also have a line hardening variable y, where it's 1 if it's hardened and 0 if it's not hardened. And beta is a risk reduction term for that line hardening. And we consider 3 different values of beta representing 3 different hardening methods. So we look at undergrounding, where we assume all risk is removed if a line is undergrounded. We look at installing covered conductors, where we assume that half the risk is removed, and intensive vegetation management, where a quarter of the risk is removed. And these values are derived from reports from the California Public Utilities Commission, WEC, and PG&E. And we also assume that we harden or manage the entire length of a line. You can see this paper by Sophia Taylor where they look at hardening portions of lines. I'm going to skip over the battery and solar constraints. We used standard models for these. Our battery is a MIP model, and you can look at our paper for more details. And for budget constraints, so we considered a range of budgets from $100 million to $1 billion. And our cost values are from reports from NREL, again, CPUC, MISO, et cetera. And one cost that I will point out is that undergrounding is notoriously expensive. Here we've used $3 million per mile for undergrounding. This is probably on the conservative side. So we could probably up this value. Okay, so we considered 2 different test cases, the RTS GMLC API test case and the WEC 240 test case. I'm only going to talk about the RTS GMLC, but you can see our paper for the results for the WEC system. So we assigned risks to each of the lines in the RTS GMLC test case, and this GIF is running through the risk values for the 2021 wildfire season, where the green lines mean less risk, and then the red lines mean the most risk. And we evaluated 3 different test cases. First, where the algorithm is allowed to place solar batteries and enhance vegetation management. Second, solar batteries and installing covered conductors. And then third, solar batteries and undergrounding. So for some results, this is a budget breakdown of how the algorithm chooses to use the budget that we gave it. So these GIFs are running through the 10 different budget values that we looked at. So on the y-axis here, this is the percent of the budget spent on the 3 different types of infrastructure investments. So any blue portion of that percent budget means we spent that much on solar PV, red means that portion on batteries, and then green, that portion on vegetation management. And the alpha value here is down on the x-axis, and I'll remind you that low alpha values mean you care more about prioritizing wildfire risk reduction versus high alpha means you care more about prioritizing load shed reduction. So this plot on the left is if we allow it to install solar batteries and do intensive vegetation management. So you can see that as it runs through the different budgets, it uses a small percentage of its budget on vegetation management. If we instead allow it to install covered conductors, the portion of the budget that installs covered conductors is much more significant, especially at lower budgets. And then finally, over here, the case where we allow it to install solar batteries and do undergrounding, it uses almost all of its budget on undergrounding regardless of the magnitude of the budget and the value of alpha. So this GIF shows the placements of the infrastructure on the RTS network for a static budget of $500 million, and this GIF is running through different values of alpha. And I'll explain what all these shapes mean. But so the pink circles here, these are load shedding circles. So the bigger the circle, the more load shedding at that bus. The blue diamonds are where solar PV is installed, and then the gray hexagons where batteries are installed. And lines that have been hardened are thick, and lines that are de-energized are dotted. So I will address the elephant in the room, which is that many lines are de-energized. And that's because this network that we tested, also the WEC network that we tested, seemed to be extremely robust. And you can kind of get a sense of how robust just by looking at the numbers of generators and relative to the number of buses for this network. So as we watch the alpha go from a small value to a high value, you can see that the number of pink circles and the amount of load shedding goes down. And one other comment I'll make about this is it's obvious that the siting selection and sizes of the infrastructure investments change based upon your selection of the value alpha. So this plot shows a trade-off curve between load shed and wildfire risk for varying values of alpha. So each one of these dots on the curve are a different value of alpha. The y-axis here is load shed, and the x-axis is wildfire risk. So the closer that you get to the origin means that you have better performance. And this gray trade-off curve is for if you're only de-energizing lines and you're not doing any sort of investment in infrastructure. So over here, these are the low alpha values where we care more about risk reduction, and over here, the high alpha values where we care more about load shed reduction. So if we install solar PV and nothing else, this is the resulting trade-off curve. We have slight improvement over just de-energization. If we install batteries and nothing else, if we do vegetation management, if we add covered conductors, and if we just underground and do nothing else. So you can see that we get the most shift towards the origin of the curve when you're doing some sort of line hardening or management, especially with this undergrounding curve in black. So we also looked at combinations of investments. So here is in this light green color, which is right here, is solar batteries and vegetation management. This red is solar batteries and covered conductors, and then solar batteries and undergrounding. And we can see that the combinations of investments are driven mostly by whatever line hardening or management selection there was. So we performed an evaluation of these infrastructure placements via a season-long simulation for the 2021 wildfire season. So the x-axis is the date in the 21 wildfire season, and the y-axis is the amount of wildfire risk in the total network, so summing up all of those risk values over the line. So this black line is the total risk in the network per day. And then we trigger a PSPS event if the total risk in the network exceeds some threshold. And we've defined that threshold as the 75th percentile of historical risk during wildfire seasons. And then these vertical lines are days that PSPS events occurred, according to our threshold, that is. So here is the resulting curve if we have installed solar batteries and vegetation management, and you can see that the wildfire risk significantly decreases during these PSPS event days, and that's again because this network is extremely robust, so you can turn off a whole bunch of lines really without consequence. And then here is solar batteries, covered conductors, undergrounding, and then if you just do de-energization and nothing else. Okay, so this last plot here is another set of trade-off curves related to budget. So each one of these lines, trade-off curves represent a different budget. So the darker the color, the higher the budget. So we have increasing budgets as you get closer to the origin. Thank you. And these curves were based on that season-long simulation that I just showed you. So you can see that the blue lines here, you get the most shift for increasing budgets, and that's when we allow solar batteries and undergrounding. So clearly you get the most bang for your buck if you're undergrounding power lines. Okay, so wrapping up with some conclusions. So we selected, cited, and sized infrastructure investments while simultaneously de-energizing lines for wildfire risk reduction. We found that undergrounding is often a favorable investment choice. And this was a very computationally challenging problem. And something that I will note is that high alpha values where we prioritize load shed reduction seem to be a lot more difficult to solve, as you can see by this plot over on the right. So what we've presented here is really pretty preliminary work. There's lots of work left to do in this area and lots of open problems. So I'll mention a handful of them. Obviously, we pose a deterministic problem, but this lends itself very well to stochastic optimization since we have uncertainty in loads and solar and wildfire risk. It would also be valuable to consider contingencies, multiple infrastructure uses we only consider right now, placing these infrastructure investments for wildfire purposes, looking at longer time horizons and AC formulation. This recently accepted CDC paper, we look at equity considerations such that we consider fairness in the de-energization scheduling, so preventing the same communities from being de-energized over and over and over again during wildfire season. It would also be valuable to look at controlled islanding, the distribution system, and we're particularly interested in these questions about scalability. We're working on some customized integer programming methods and working with some MIP experts to make these problems more tractable, looking at bound tightening and decomposition methods, cuts, et cetera. And then we're also interested in using instead some conservative LP battery models, and Mads has a paper on that, which has been very useful. And lastly, as I mentioned, these networks are extremely robust, so we need to work on developing networks that are specifically tailored to these types of problems, that are geolocated in high wildfire risk areas and aren't as robust as the RTS network that I showed here. So that's it. So thank you so much for listening.
Okay, time for one question. Go ahead, Mladen.
Yeah, Mladen Kizunovic, Texas A&M. I'm sorry, I have maybe two questions, one after the other. One is, I got a little bit lost. Are you talking about transmission, distribution, or both?
Just transmission.
Just transmission?
Yeah, yep.
So is that the major cause of these fires?
So most wildfires are sparked by distribution, but looking at the transmission system is also valuable. For the Camp Fire in 2018, that was sparked by transmission lines. But we are interested in looking at distribution as well, but we started with the transmission system here.
The other thing is, this concept of risk that you are talking about, it's dynamic, it's changing. So I somehow lost track of how do you, based on a relatively short period of time, estimating risk, you're trying to invest into the infrastructure. I mean, you would resort to some risk analysis that is dynamic, that allows you to, switch things and so on based on how risk evolves. If you're looking at the risk as a measure of something permanent, as an installation improvement in the infrastructure, then the horizon has to be much longer.
Yeah, I totally agree with that. And that's one of the reasons that making these problems more scalable is really important, because we need to be able to consider longer time horizons and consider, uncertainty in the risks. And here we were only able to do a deterministic problem and just look at one representative day. But I definitely agree. We need longer time horizons and incorporating that uncertainty in a better way. Yeah, thank you.
Thank you.
Thank you, Lisa. I would like to ask all the presenters, can we get our first presenter on the line? Please come forward and take a seat. We're missing a mic here. Do you still have it? Oh, here it is. Okay, the floor is open for questions. So let's start with you, Yilio.
Please go to the microphone. That microphone, please. You want close to the computer because otherwise.
Yeah. Very good. Okay, so we'll use this, I guess.
All right, Iluliu, question for the wildfire. So do we have field data that showed that the energizing line actually reduced the fire occurrence? Has that data been, factored into the study? That I think that would be really significant, to have that proof as well. Yeah.
So just to confirm, so you're asking if we have real data that shows that de-energizing lines is valuable. Is that correct?
That's correct, but also I like to tie that to your study. Do we have a way to verify, the calculation corresponding to the field observation as well? I know it's difficult because only 10% of the real big fire was caused by, transmission system.
Yeah. So the conversations that myself and my colleagues at Argonne have had with utilities like PG&E and SCE, they say that any line that's energized poses a risk for sparking a wildfire. So I don't know if there's a database or whatever you're alluding to as far as...
Or some rough statistical estimation of the reduction.
Yeah, so I'm not aware of anything in the literature like that, but if you're aware of it, I would be very interested in seeing it. But yeah, sorry, did that answer your question?
Probably not literature, but mostly their observation recently, because they didn't start the line, the load shedding.
Please use the microphone.
Yeah.
So that we can record this.
Yeah, it will be difficult. So please, when you ask a question, stay here until you finish the direction and so on. So you want to come back again, or?
All right.
Is it working? I'm not sure it's working.
It is working.
Yeah, by the way, I'm able to hear even remotely, so it's okay if people don't walk up front, I think.
Is this a good idea?
No, you have to go to that microphone so you can get
Not even with this?
No, because the microphone is open.
Okay, so I'm asking the question one more time, so sorry I didn't make it clear. So the study showed, how the fire reduction can be achieved by de-energizing lines. But my question is, do we see any observation? Because PG&E had quite a few, line de-energization recently. Do they see statistically or roughly there's some reduction observed? I doubt if there's paper yet, but no. Did they observe fire reduction in some way because their line de-energization? Yeah.
So actually, Lena, in one of her recent presentations, quoted PG&E where they said that during the 2019 wildfire season, they avoided 100 potential ignitions due to de-energizing lines. But I don't know where those numbers are coming from or what type of simulations they're doing to get that 100 avoiding 100 ignitions.
Sit over there. Yeah. Lena wants to say something about it, so go ahead.
Sorry, I'm not sure which microphone to go to right now, so I'll just try here. Yeah, so sorry, I just wanted to kind of comment on this also. So Alyssa, of course, did a very good job with it. But yes, so PG&E, I think, is very, they are looking, they have to go and re-inspect every line every time before they re-energize it. And so the statistics of the 100 wildfire ignitions that they said have become avoided is based on, in 2019, they had this largest public safety power shutoff to date. And so they shut off power to something like 3 million people for several days, which is, of course, hugely disruptive. And then at the same time, they did observe when they went out and inspected the lines that 100 of the lines had damage to them that would likely have caused arcing and could then also have led to a wildfire ignition. So I think it's like without question that de-energization is effective, but like the question that you're asking, what is the trade-off between that large-scale de-energization versus the number of fires that might have been, that I think is still up in the air, and that is like exactly what we're trying to research, right? And I want to also mention that conversations with Duncan Callaway at UC Berkeley, I know that they have access to some of PG&E's internal data on this, and they are trying to also analyze, like both the probability that you would see an ignition from lines. I think they've also had a recent publication on that, and also try to so leveraging more real data into this process. So I am like very excited to hopefully that we will have access to more of this data soon.
Thanks. Very good. Thanks for all the discussion, and we haven't brought the lawyers yet in this question. Okay. Next question, Claudio. You want to come forward here?
Yes, I have to. The reason for this is that the microphone for the person online is there. No,
he cannot hear us.
Yeah, I'm
no,
able
he
to
cannot
hear
us.
just fine.
So the microphone is here. Okay.
Nice work, Sandeep.
No, he cannot hear. Anyway, we already tested this. So, sorry about this because we had to improvise. Unfortunately, this happened the last minute. Otherwise, we would have planned better, okay? But so, please help us. Don't fight us. Okay, so the question is, can you hear, Sandeep, by the way?
Yes, I can hear. I can hear from any point in the room, no problem.
My question is for the low-frequency AC system. I found it quite interesting. Now, I'm curious about the cost, though. You mentioned that you can use the same cables. I wonder whether that's quite true, because I think that some characteristics will change, might not be the same. More losses, I presume. Also, the question of the transformers and all of this together, how would this compare once you compare with DC? Because I guess you get similar things. So is it justifiable? Why don't you just go to DC? Can you comment? Thank you.
So just to clarify, the first question about the cables, you can use the same cables as 50, 60 hertz or as DC? Which are you asking?
Yeah, as you lower the frequency, I don't presume that those voltages, the cables might not necessarily be the same. We might have to derate them. It might not carry as much current because, the frequency has changed, has reduced. So the question is whether the cables are going to be the same. Transformers might necessarily not be the same because the frequency has reduced. So when you put all of this together and you compare with DC, would this be justifiable to go to lower frequency? Why not just go to DC when you show that the results were similar?
Okay, yeah. So there are a few factors to think about, different permutations of the problem. Are we going from an existing 50 or 60 hertz AC system to a low frequency, or are we going to build an entirely new corridor with low frequency or DC? If we have all the options, then the question maybe becomes a little bit different. But on the first question about cables, as far as I know, the cables are fairly equivalent. We're modeling the properties. So the model that I presented goes down to the dimensions of the cable and the material properties, the electrical and magnetic permittivity, those types of questions. So we can take that detailed cable model and we fit that into our approximate model and into the OPF. So we're accounting for those types of
Sure, I wasn't talking about the models, but the physical infrastructure. insulation, those kind of like transformers. But nevertheless, it's okay. Thank you.
Sure, yeah. Just to follow up on the transformer question, that I think ideally we wouldn't have transformers in a low frequency setting because the size becomes so large, and so we can design the topology of the system to accommodate that. But if necessary, we can accommodate large transformers. I think maybe the takeaway here is that we need to do a detailed economic analysis for specific conditions.
Very good, thank you. Well, MISA has instituted a new procedure for the questions. We're going to have a queue here. So we're not going to use the hands. So if you want to have a question, to ask a question, please come and form in the queue. So MISA, go ahead.
Misha Chertkov, University of Arizona. Crazy question, and I'm not sure it's appropriate, but low frequency. In fiber optics, there is very efficient way for communications, of course, to use multi-frequency, the same fiber. Is there any advantage in using at multi-frequencies, not at single frequency? Yeah, ask Lina, and she approves this question.
That's a great question. I don't know of any work that has been done on that before. The closest thing I can think of is I think in Germany there are some transmission towers that have 50 hertz lines and DC lines on the same towers, and there have been some studies about interactions between those. I think there are some issues with harmonic interactions, which I would expect may occur when you combine frequencies, but I really haven't heard any conclusive studies about combining frequencies on the same conductors. But that's a great question.
Thanks.
Hi, Robin Priest, University of Manchester. A question about the wildfires for Alyssa. You mentioned on the last slide that controlled islanding was something that you were going to look at, but did I interpret your results correct? It looked like it was cutting the network into loads and loads of little islands already. And is that how that would actually be implemented at a transmission level? And if not, how would you constrain against that to try and avoid forming those islands during this kind of problem formulation?
So the results that we showed really, because you're de-energizing so many lines, it really chops up the network a lot. PG&E actually allows islands to form, in the transmission islands to form for wildfire de-energization, but I imagine it's just not any island to form. So we were looking into ways inside the optimization problem such that we can say, okay, these are the islands that we will allow to form. We haven't come up with quite a good way to do that yet, but it's something we're working on.
No, thank you very much.
Jochen Stiasny from DTU, and it's about convex inner approximations. So they're not unique, right? So because you could just choose a smaller set that would be more conservative, and there could be different bounds. So how would you choose between different options and would that affect the performance of algorithms that's built on it?
So you're referring to the selection of how much reactive power to select from each of the...
No, rather the shape of the bounding box. So you can imagine different bounding boxes.
That's right, okay. You're talking about the hypercube.
Yeah.
Okay, so you can, okay. So the solution we get from solving to find the hypercube, it is a convex program, you get a solution.
So that has some objective in
It does. Okay, that's right. Okay, now I remember. So you have to, so in your objective function, when you determine your reactive capabilities from each of the individual turbines, you can weight them in different fashion.
Yeah.
And so that weight would prioritize where you would prefer to get most of your reactive power from.
Okay.
And so you could weight it from the back of the network to the front of the network. And so that would be the prioritization approach.
All right.
Good question.
Next question. Go ahead, come forward. Yeah.
No,
come forward.
Come up. I'll ask the question really quickly. So, Alyssa, it was a really, really nice presentation. You started out in your presentation saying there will be 10,000 lines that need to go underground. And I think you concluded saying undergrounding was a good choice. And so have you talked to PG&E about how they should choose which of these 10,000 to start with to underground? So.
No, we haven't talked to PG&E about that, but we would like to have more information about the network. So right now, PG&E, they de-energize lines based on the condition of the line and how old the components are and all these various things, information that we don't have access to. But I think if we were able to have access to more information and also make these problems more scalable and have access to their real network and whatnot, that would be a good conversation to have with them. But yeah, it would be a valuable conversation to have with PG&E and potentially get more information.
Very good. Thank you. Go ahead.
So I like this idea from Spiros from Technical University of Denmark. I like this idea about this multi-frequency transmission or distribution. And we are always trained to think the limitations somehow. So I wonder, yeah, this would be a nice discussion. I think it's a nice discussion to think about it. But so there are two things. The first is communications does that because they want to distinguish the signals, right? They send different types of information. Here it's about power. So I don't know if it makes sense to have different frequency, since everybody's interested to get the energy. So maybe, yeah, Mats maybe can have an idea about that. The second is that transformers. I think only with power electronics you can actually have so otherwise you have to have separate transformers for separate frequencies because they are optimized usually for different frequencies. So these are maybe ideas that maybe people can. Yeah.
Anybody?
Yes. So I guess thinking about the advantages of this multi-frequency idea, it's something that hasn't really been thought about. So it's an interesting thought experiment. But I think I agree with the concept of maximum power delivery on transmission lines is what we're after. And I'm not sure how that would improve the maximum power that we could deliver. We would have to look at the advantages of low frequency AC are due to the mitigation of angle constraints and the thermal limits, really the interactions with frequency and the capacitance and inductance of the lines. So we would have to have some multi-frequency models for the impedance of the lines, which I'm not sure if we would get advantages, but it may be worth thinking about. And then the concept of transformers and where we place converters. I think these networks do rely on having quite a few of these power electronics devices. They benefit from that, but it's also a very costly aspect of these systems. But I think there can be some advantages looking at staying with AC systems where we retain the reactive power and voltage angle, which I think have some good control properties that maybe we don't get with DC. And the protection equipment is also a factor that I'll mention again.
Thank you very much.
So my question is for Sandeep. So you're very missed today, or you really missed that you're not here. But thank you for presenting. In your presentation, Sandeep, I think if I remember correctly, you were showing a 15% change in your parameters would give you a 2% change in your power. Is that right?
You are muted.
You're muted, Sandeep.
You are muted.
Sorry about that. I wish I was there also. So, no, I don't think that the change in flow is only 2%. It's more than that. It depends on the specific example and also how far away the lines are. We were looking at up to about a 20% change in the parameters, and I think the flow changes were anywhere between sort of 2% to about 15% or so. Ali, do you remember any better than me about that? So.
I think what you said is correct.
So I don't know if Ali is there.
He approves. He approves of your numbers.
Okay. Yeah.
And
okay.
Just maybe one follow-up question. If you were to replace your facts, maybe employ a phase-shifting transformer, how would that be different?
So my honest answer is I don't know, right? We would have to work through it and develop the model for that and do the analysis. We chose to focus on the fax devices because they're kind of a direct route to think about the impedance change, right? But I think there is probably a possibility that a phase shifting transformer would also work. It's a good idea and something worth trying there.
Okay, thank you, Sandeep.
Next question.
So João Peças Lopes, University of Porto. This question is for Mats. So have you thought about using the approach you presented for grid code compliance verification in the point of common coupling? Because usually grid codes, they require the verification of these PQ curves, PQ capability curves. And in this way, usually the system operators, they do not allow wind farms to be connected unless they verify those curves. And I think this tool can be a possible solution for verifying that and helping in that verification.
So that's a really good question. After we got the preliminary results, we met with the transmission company in Vermont, and we have a wind farm. And we did ask them for how do they characterize the reactive capability of this wind farm. And it led to a number of conversations, but in the end, we actually did not get an answer. But that's something that's worth pursuing.
Yes.
Exactly.
Right.
Yeah.
And also, you need to take into account that nowadays, most of the power converters of the wind generators, they can also operate as static compensators. So they do not need to, I mean, if there's no wind, this doesn't mean that they are off. They can be connected and providing reactive power support.
So we did assume that in our models.
Okay.
But getting the industry standard for how to characterize these curves would be quite valuable.
Yes.
And so we'll continue the march.
Okay, thank you.
Any other questions? Okay. We started 5 minutes late, so we still have 3 minutes. So I will ask a question. I would like to ask a question of Sandeep. I enjoyed the presentation and using the matrix inversion lemma to compute the modulation of the parameters onto the solution. That's a very good idea and so on. My question is the following thing, that is, normally we do not modulate the impedance. Basically, we inject a phase shift and so on. Is there an equivalence between injecting a phase shift in a circuit and changing the impedance of because changing the impedance is very difficult. You can do it, but it requires redoing the line, basically. Is there an equivalence in what you're doing with the actual physical insertion of a phase shift?
Yeah, so that's an interesting question. The introduction of a phase shift, like if you work through the model for the power flow in that situation, the approximation as a change of impedance, I think it's indirect. It's not exact. I would have to work through this a little bit more carefully on paper, but I do think there is a possibility to model it that way. And so there is an equivalence with regard to this. Again, Ali, you're more fluent on the power electronics side of this. I'll let you indicate your thoughts about this also. So.
Very good. Thank you very much. Well, thank you very. Okay, go ahead.
So as Sandeep mentioned, we didn't directly work on how exactly we would find an equivalent between the phase shifting and the change in the impedance. But it's actually one of the things we are working on. That and also even converting lines to whether HVDC would really help. But with newer technologies, I do want to say that that is actually becoming a reality. I mean, of course, reconductoring the lines would be a solution, but also distributed fax devices, right? Things that, say, smart wires, for example, does.
They still inject the phase shift and not really the non-modulated impedance.
DFAX essentially injects a voltage, right? Injects the voltage, and the equivalent would be seen essentially as a change in impedance.
That's what I'm asking. That's the question. Is it equivalent change in impedance versus inserting a voltage that basically is a phase insertion?
Yeah, but my point is the effect of that injecting that voltage is exactly seen as a essentially change in the impedance of the line, because that voltage is always going to be 90 degrees phase shifted with respect to the current. So. Which is a bit different. I mean, if you're comparing that to the traditional PARs and so on.
Thank you.
Thanks.
Well, I would like to thank all the presenters for all the papers. There is more questions? Okay. And lunchtime. Let's give a round of applause to the presenters.